Look at this beautiful precipitate. This is silver cyanamide, and it's how we'll be testing the purity of the calcium cyanamide we're synthesizing today from scratch. Now, this compound is a crucial precursor for my future projects, but finding it on the market these days is a real headache. So today we're converting quicklime and urea into this exact precursor, analyzing its concentration, and using this experiment to show you how to streamline your workflow with the openchemdb.com lab journal. Here is how it works. So I need calcium cyanamide as a precursor to synthesize guanidine and aminoguanidine. As I mentioned, buying it as a fertilizer is getting harder and harder. We'll run this synthesis in two stages. First, we'll produce calcium cyanate from urea and calcium oxide, quicklime. Then, we'll calcine that calcium cyanate at 800 degrees Celsius to get our final calcium cyanamide. Let's start with the calculations. These days, I calculate reaction stoichiometry right inside the journal tab on openchemdb.com. Here it is. Since I'm logged in, you can see my personal lab journal. You don't actually have to log in to use the tools. Everything works exactly the same. You just won't be able to save entries to an account. First, let's draw our starting materials and the product. The molar masses are calculated automatically. We'll be running the reaction based on this equation. We need 3 moles of urea for every 1 mole of calcium oxide. Let's enter these molar equivalents into the journal. I'll be using 500 grams of calcium oxide for this reaction. So I'll type that into the mass field, and the system automatically calculates exactly how much urea I need to weigh out. You can also fill out other fields like the procedure notes. What's really convenient is that you can save attachments here. Papers, spectra, photos, and even short videos. Let's hit save. Now this entry is safely stored in my lab journal, and I can easily find it via search anytime. Now let's move on to the actual synthesis. We mix our calcium oxide and urea together and start heating them on a hot plate. When the reaction kicks off, it foams up heavily and always tries to escape the pot. Keep stirring it. After a while, the mixture thickens and the foaming subsides. Eventually, it solidifies completely. After about an hour on the hot plate, the cyanide synthesis is complete. Here's what it looks like. To be completely honest, this is a mixture of cyanate and cyanurate, but it doesn't matter for us because it will all convert into calcium cyanamide during the high heat stage anyway. The second stage is the synthesis of the calcium cyanamide itself. To do this, we need to heat the cyanate to about 700 to 800 degrees Celsius without access to oxygen. I've seen people do this reaction in a campfire multiple times with decent success, but since I have a muffle furnace, I'll be using that. Here's a stainless steel crucible. A lid is absolutely mandatory here to restrict oxygen flow. We pour our cyanate into it, pop the lid on, and put it in the furnace at 800 degrees Celsius. The patent calls for 1 hour at 800 degrees Celsius. However, when I opened the furnace after an hour, a bunch of gases were still escaping, and strangely enough, they were flammable. So I closed the furnace and kept it in for another hour. After that second hour, the gas evolution pretty much stopped. I turned off the furnace and pulled out the crucible. Here is my calcium cyanamide. I ran an IR spectrum on it. This broad peak right here is characteristic of calcium cyanamide, which confirms it's present in the mixture. Now I want to determine its exact content in the final product. You can do this with pretty high precision via a precipitation reaction that forms silver cyanamide in an ammoniacal solution. So I took a weighed sample of my calcium cyanamide and added water. Then I added nitric acid drop by drop until the solution became acidic. The cyanamide dissolved almost completely. I filtered off the undissolved parts. Those are just impurities. This gave me an acidic cyanamide solution. Next, I dissolved silver nitrate in water and added an excess of ammonia. Note that I used an excess of silver nitrate relative to the cyanamide. Slowly, I poured the ammoniacal silver solution into the cyanamide solution. Instantly, a precipitate of silver cyanamide formed. I filtered the precipitate and weighed it. Based on these calculations, the yield came out to 62%, meaning the calcium cyanamide content in my product is 62%. That's a pretty solid result. According to the patent, the maximum yield should be around 80%, but that's using pure cyanate. In our case, the cyanate made from urea and quicklime wasn't perfectly pure, so a 62% yield is totally fine. That's all for today. See you next time.